I'm Kostas, this is Aram, you probably know him. You can get fun later on pronouncing my last name. This is speed and size optimized implementation of the present Cipher. It's too big, let me explain it really quickly. So, this is a project that came out from the Kerckhoffs Institute. We are an institute which mainly is a collaboration between universities, Nijmegen, Kostas, and Verstegen. So, we have a security institute, and I'm currently a PhD student in the... Oh, some more.
Okay.
Alright. So this is, I'm currently a PhD student in the digital security group in Nijmegen. So this is where I work. And I mainly work on lightweight cryptography and Cipher implementations. So, lightweight ciphers. This is a very easy question. What is the main functional requirement for a cryptographic primitive? Well, somebody tells you, make me a cipher that encrypts stuff. Well, this thing has to be secure. Huh? So, like 20 years ago, people were just thinking about security. That was the basic and most important consideration. Other stuff like speed or efficiency came in second, but the main stuff was to create an algorithm, like in the 90s with AES, that was fairly secure. So, this is how it was, but is security the only requirement in cryptography? It's the most important one, so I'll give you that. But recently we have seen what they call it, people like calling ubiquitous computing. So we have cell phones, we have RFID tags, we have sensor networks, and they all need to communicate, and probably they also need to communicate securely. So you need to grab a cipher and put it in that tiny little device. And then you search around for a cipher, and they tell you that the best cipher around is AES. AES is a very good cipher, and there has been lots of work trying to make it really compact or really fast or squeeze it in tiny hardware. There has been lots of research and lots of papers and people doing that. But truth be told, AES was crafted with security in mind, so only security. So then, the big issue is that we need another cipher that is custom made for these tiny applications. And somewhere in the 90s, I think again, there was this cipher, they called it key lock, and it was in South Africa. So the industry wanted a cipher, and they didn't want to put AES inside, or AES was still new at that time. And they wanted something really compact, and they made their own cipher. They said, well, that's good for our application, because we have a really tiny application. And they didn't do well, and the cipher was broken. This happens from time to time. But what is the moral of the story? Is that people try to do stuff on their own, and they try to fill in gaps that are still open. So we only had AES, and then they wanted another cipher. But hopefully that's not the case today. So like from, I would say, 6 or 7 years ago, people started really thinking about lightweight ciphers. So instead of, previously we had only security, and now we have like a huge design space that is also the hardware speed and the hardware size parameters. So somebody that sits down and makes a cipher, he won't only think about security, but he will try to make trade-offs between those three, like Bermuda Triangle, like design space. Because it's hard. I call it Bermuda Triangle because it's kind of hard to figure out what happens in there. And there were quite a few ciphers that came out here. So Present, Catan, Klein, perhaps you have heard them. They're all really tiny and custom made for small applications. For security, we had AES, and there is also one new parameter that is speed in hardware, and there are also ciphers for that. And this is already a complicated situation, huh? But in order to make it more complicated, we also have software performance, because this stuff mainly refers to hardware size or speed. And now, software performance also interacts with these three parameters. And this is the big question. Let's go to the previous slide again. Does one thing imply another? So I make a cipher, it's really compact in hardware. Does this imply that it will be compact in software? Or vice versa? And this is not the case. So if you make a good cipher for hardware, there is absolutely no guarantee that you're going to go well in software. So this work is about a tiny cipher implemented in AVR, so that is almost software. It's an assembly language, but it's still software almost. And we have the tiny family of devices. That's all Arduinos. Actually, Arduinos are at megas, so they are more powerful than the thing we're using here. But we used a tiny 45, which has a flash memory, a strong memory, and a clock. And it has a set of instructions, some registers, and another 16-bit address space. However, let's take a look at the address space. Let's make a small tutorial about these devices. So you have R0 up until R31. These are the registers of the processor, and these registers up until the first line, they are mainly registers that are I should call them internal. They cannot access memory. And then the rest of the registers can access memory, and in the end there are some registers that are used to address memory. So pretty basic assembly. Then comes some input-output registers, and finally the SRAM of the device. You will find pretty much the same structure in most Arduino chips. Perhaps they have different bank numbers in SRAM or something similar.
The beginning of the MS layout is the same on all the chips.
Yeah. Perhaps, yeah.
You have more I/O or a different location for your SRAM offset.
Yeah, there are differences, but this is the main idea, and it pretty much applies. So people usually write code in C in order to do AVR, but we write assembly because we want it to be really fast. So also
and really
very and really small. Aram is going to talk about small things. I
ain't even mad.
Okay. Yeah, by the way, the implementation is either very fast or very small, or fast and slow, which is a bad boyfriend. Okay. Anyway, the device can do pretty much all stuff you expect from assembly, like loading stuff from static RAM, loading stuff from memory, that's LD and LPM. It can shift, it can rotate, and then you can pretty much get the instruction set that you would find in any x86 assembly language with some twists. So, present Cipher. This is the Cipher implemented it, and the idea was that we wanted to make it really fast, and I wanted to make it really small. Both things are important. Both things because in some places we are extremely constrained, cost-wise, or in some other case we have to reply fairly fast, so we do something like this. So, what is present Cipher? Most ciphers, or lots of common ciphers, are substitution permutation network. So the idea is that, there is a plaintext and there is a key, and we start and XOR the key with the plaintext, and then we go through two operations. An S-box layer, that's the substitution operation, and a P layer, that's the permutation operation. And these two operations will go on and forth, and XORing as well for 31 rounds. In the case of present, in the case of AES it's 12 or 10 or 11.
Depends on the key size.
Yeah, depends a bit. And in the end we ended up with a ciphertext. So I also have this small visual reminder here. So this is the substitution operation. I'm going to talk exactly how this is. And this is the permutation operation. I'm also going to talk about this. Right now I'm focusing on both of them. So this is encircling both. So if at some point you get lost, it's probably going to show what I'm talking about. Okay, so people before that, as I said, they used C language, and they did fairly, I would say, fairly slow, so lots of cycles per byte, and fairly big size Cipher. So if you want to do it really well, don't use C and AVR GCC. So some other people did it, and they ended up here. They used assembly and a set of nice techniques. And that was the state of the art a year ago when we first started on that project. So from now on, I'm going to sit down and explain step by step all Cipher steps. So add ramp key, substitution layer, permutation layer. So I'm going to pretty much explain in assembly how I did this and the idea behind. So add ramp key is fairly self-explanatory. You have 64 bits, and you XOR 8 bits with 8 kit bits, and 8 more, and so on and so forth. That's very easy. And then you move on to the substitution layer. So what people do in substitution layers is they use the S-box. You've probably seen the AES S-boxes. These are slightly different. So in AES Cipher, we use 8 bits inputs, 8 bits output. Now we're trying to limit it because it's a lightweight cipher and it's a 4-bit input and 4-bit output. And it gets substituted exactly as in this table. So if value 2 comes in, then 6 goes out and 4 comes in, and so on and so forth. And now, if I may ask a question, I'm giving you this table and I'll tell you do it, implement it. So how would you implement the S-box? Would you, in any language, what would you do? In C language or anything you like, please?
I have a lookup table for the S-box,
Exactly.
and then we go byte by byte, but we want to do 4 bits at a time. So we use like AND operation to mask the lower 4 bits, use it as a lookup index. And then for the high nibble, we shift to the right by 4 bits, and then we use it as a lookup index.
That would be very nice solution. and it is. If somebody tries to implement it, it's going to do this, and it's going to be fine.
That's the next slide, I think.
Yeah. So in software, you're probably going to put the lookup table in memory and then look it up. But let's say you want to do hardware. If you want to do hardware like a really compact application-specific integrated circuit, you're probably going to go to actually make the circuit. So you're not going to view this as a lookup table. You're going to view this as a Boolean function with 4 bits input or 4 bits output and or XOR gates in the middle. And you're going to create a circuit based on that. Alright, this is my first point, that there is difference between software and hardware. You could try also lookup tables in hardware and FPGAs, but that's not important. There are differences, and this differences propagate in a different way, and I'm gonna talk about this. So, yeah, 4-bit S-boxes. Peter already found the answer to that. He's probably gonna do something like this. He's gonna ZL and Z highs at some point is the address register. So you load an address there, and then it fetches that address from the RAM. So
right. Oh yeah, the RAM. Is
the
that the flash pointer?
Yeah. Either
access the RAM point.
It can the register can access either the RAM or the flash. But here we access the flash because you do LPM instruction. So you grab it, you put the correct address in the memory, then you do an LPM for the low nibble, and then you also do the same thing for the high nibble, and then here we swap the 2 nibbles so that they're exchanged. You will XOR them and mask them out and shift them. That's also the same thing, and then you will end up with a substituted value. And this is okay, but you can do slightly better. So you have an AVR is an 8-bit architecture, AVR tiny. So the idea is that every time you fetch data from the memory, you fetch 1 byte, 8 bits. So in here we fetch once, we fetch 4 bits, and then once again we fetch 4 more bits. So that's not really efficient. Perhaps you should figure out how to do it on its own. And the idea that came out, that's not our idea, but we also thought of that, was to actually make a square S-box. So if the value is 0 in the high nibble and 0 in the low nibble, then it's going to get substituted by C and C. So if you take a look, 0 goes to C. And then 0, 0 goes to CC. And we have all the list of possible combinations. But now we don't have something like this symbol, like a single line. You have to store this whole square S-box table in the SRAM or in the flash. Usually in the flash because the SRAM is fairly small. And so it's 256 bytes compared to the previous one, which was just in line. So how big was 8 bytes? Yeah.
Well, depends if you
8 or 16 bytes versus 256 bytes. So you already see the trade-off, huh? I used like substantially more memory, and I ended up with something that was substantially faster. And it substitutes 1 byte at a time, and there is no longer need to swap the nibbles, the 4-bit parts. So you just use the address register, and then you do LPM that loads from flash, load program memory actually, and it works. So once I shift up towards the permutation layer. So this is a whole overview of the cipher once again, in case you forgot. So all these things here are bits, and all bits get XORed with a key all over this small XOR gate over here, and then they go through the substitution layer, all the S boxes here up until the end, and then there is this permutation layer starting from here ending to here. So what we observe about permutations is that they are bit-based. So every bit gets permuted and somehow creates diffusion, all in a very specific, complicated but specific pattern. So, once again, we saw how we constructed the substitution layer. How do you construct the permutation layer? Now, this is a bit trickier. Peter, you want to give it one more shot?
I'm blank.
Yeah. But don't look at hardware, look at software. You could just mask a single bit out of the register and then shift it and then put it in the correct place. And then it once again, 64 bits in total. It will take a while. That is probably what you're going to do in software. Or there are other solutions, and I'm going to talk about it. In hardware, if you do this in hardware, you don't have to do anything. That's the beautiful thing about hardware. You just rewire everything. So from one register, there are some lines starting. They go that way, and then they go to new registers or to the previous one. They feed back. And you don't have to do anything at all. But the big issue about the present cipher is that you have to have a good permutation performance. If you end up with a good permutation layer in terms of speed, then you're also going to do fine. So now I'm going to really focus on the permutation layer, that layer, and go for an in-depth analysis. So, as I said, you can implement the permutation layer with masking and shifting. So this is register A, an 8-bit register, and you want to grab bit A3 from the register. You just mask it up, here's a 1, and then you shift it where you want it to be shifted, and then there is an OR again, and you deposit it in another register. So that's how you grab bits around. This is what I would probably do if I was writing x86-like assembly. But the issue with AVR assembly is that shifting is proportional to the argument. So, what do I mean by that? Here you grab it, you shift it, and then you deposit it back. But here in the shifting, if you want to shift something like 5 positions to the left, that's going to take 5 cycles. If you want to shift 4 positions to the left, that's going to take 4 cycles, and that eventually is killing us in the long term, because if you do that 64 times, these operations seem really unimportant on that if I do it once, but if you do it many times, then it kind of hits you. So, I think we have established that AVR is bad at shifting, because although you can add in one cycle, you can multiply on 2 cycles if you use another AVR. You can XOR, OR, and do stuff like that in 1 cycle. But for shifting, it's always, you shift 3 positions, 3 cycles, 4 positions, 4 cycles. So, I'm not the only one that observed it, and the guys who made AVR also observed it, and they came up with 2 instructions like BLD and BST. And what these instructions do, which they're all 1 cycle, by the way, so you want to extract and deposit A3 from this register, register A, to register 3. So with BLD, you grab it and you put it in a flag. And with BST, you deposit it back to the position that you want. So instead of masking and XORing and shifting, especially the shifting, you do this. And this is like 1 tick from here and 1 more tick from here to here. So, instructions BLD, BST cost 1 cycle. So if you want 64-bit permutations, 128 cycles. So twice.
1 cycle? So it's a 1 cycle move to the flag and then to the deposit?
One to the flag, 1 from the flag to the deposit.
Yeah, okay.
And you can specify exactly where. So grab it from register A, position 0, 1, 2, 3. Then put it on register B on position 6. So in 2 ticks. So I gave you a way to implement the permutation there. You also have a way to implement the substitution there with lookup tables. If you do that, you're going to end up with a cipher speed of around 10,000 clock cycles. And that's what people did before. So, it's a bit blurry. So we shifted back our attention, that was the first thing we did, to the whole substitution and permutation layer together. So we had a lookup for the substitution table. Perhaps we could combine the substitution with the permutation there. That was a bit tricky, but some people found out about this and they published it. And from then on, we grabbed it and we adapted it for AVR. So that's a big thing. So let me show you that way. So you remember I had lots of substitution boxes. Now I'm just going to zoom in the first and the second substitution box. So here is bit input 0 to 7, so the first byte of the cipher, 8 bits, and all of these bits go in to the present to the S boxes. And only so bit 0 goes in, gets substituted, and then gets permuted to bit position 0. Bit 4 goes in, gets substituted, and then gets permuted to bit position 1. So this is the idea that, wait a minute, okay, a single input byte will contribute 2 bits to the output. So we crafted lookup tables that used this idea. They were bigger than before, but they looked up byte after byte, and for every byte they gave us a 2-bit output that we later combined on. This took even more space than before, than the square S boxes, and if you do that, you're going to end up with 8,700 clock cycles, which is better than before. And that was 6 months ago, 7 months ago.
Over the summer.
Over the summer.
Yeah, about June, I'd say.
Alright, so I've offered a solution for the permutation layer that use the instruction set architecture of AVR with BLD and BST. I offered a solution that uses lookup tables and merges the substitution operation and the permutation operation. This is as good as it gets, and I thought that it's as good as it gets for a long time. But then there is more space for improvement if you think different representations. What do I mean by different representations? So, has anyone ever heard bit slicing as a term? Ah, okay, then it's going to be easier. So, assume I give a small tutorial for those that haven't heard of it, but assume here that there is a register. And this is bit position 0, this is bit position 1, 2, 3, 4, 7. Okay? And I just need you to put bit A from this position to this position, and bit B from this position to this position, so pretty much the arrows. So, if you are doing this like Peter said, you are the star of the presentation.
Yeah, we'd probably use an end mask to get the value
an end mask
of
and then grab it and do it. Yeah, and that will take a bit, but if you looked at it that way, so instead of storing it in a single register, you use 2 registers. And I call this register R and this register U. Then somebody tells me, permute A with B, swap them in positions. I don't need to do anything. That's the point of this slide. Previously I was calling this position 1, register for position 1, and this register for position 0. Now I just need to keep in my mind that this is register for position 1, and this is register for position 0. So that's the idea of bit slicing. You put everything in registers, and that's the slice concept, that you no longer have to do permutations. Permutations are for free now. So,
as long as you have plenty of registers.
As long as we have plenty of registers. In our case, we didn't have plenty of registers. We put everything in the SRAM. Talk to you about this. Alright. So permutation computation is simple register renaming. So you just call register different names and you move on with your life. So in principle, 0 cycles. In practice, it was a bit more, but still, it's an improvement. Okay, some side effects. First of all, the permutation layer has lots of permutation. You see in the bit operations. And we used bit slicing to compute the present layer. So previously we had 64-bit input. And that means 8 registers. Now we have 64 8-way bit slice registers. So much more. It doesn't fit into the registers. We only have 32, so I use the SRAM. So you have register 0. That is in fact bit position 0. And register 64, that is in fact bit register 64. So if I grab this bit here, that means bit position 0 for block 2. What do I mean? There is what we call 8-way bit slicing, because there is an 8-bit register. AVR has 8-bit registers, and there is 8. So every time we store something in here, we in fact store 8 bits in parallel. So every time you permute a register with another register, you swap them. You in fact do what we call single instruction multiple data. That means you view this as single bits running on a single processor in parallel. So, permuting the register results in 8 parallel bit permutations, or adding or XORing two registers together means that in fact that you XOR bits together that way. And because of the fact that it's bit sliced, all the permutation of of present becomes simpler. So, the last slide talks about how I shift my attention from permutation layer back to S boxes. So, before we talked about it, I could just use squared S boxes and do the substitutions. Or even 4-bit S boxes and do the substitution. But now, if you have 64 registers, how are you going to substitute 64 registers? You should either start extracting bits or craft lookup tables that have size 2 to the power of 64. I wouldn't even care about doing that, not on a regular computer, not in an AVR. So, once again, we borrowed a function from hardware. So if you remember in the very first slide, I asked you, what is it? How do I compute the S box? Can I also compute it with a Boolean function? And then it turns out that I can. So instead of computing the substitution layer with a lookup table, I use a Boolean function. It's a 4-bit input, 4-bit output. You can craft a truth table, and you can get an output. And that is the nice thing about it. Bitslice kind of fits really well with Boolean functions if you have a good Boolean function. Alright, so you need to craft a Boolean function, and this needs to be minimal. So if you ask Aram for AES, can you get me a minimal Boolean function that represents in either delay or space or anything? It's NP hard. So the problem of circuit optimization is NP hard. So it's kind of hard. And so some people came up with what they called the Boyar-Peralta heuristic. So these 3 steps that you can read later on are pretty much some steps of a heuristic in order to craft a Boolean function that fits our needs quite well. And on top of that, there was another approach from Courtois who extended this heuristic in order to apply for present. And they resulted with some really nice, almost optimal, I would say, S boxes for present. And we used those specific in the implementation. So there is quite a big, bunch of theoretic work that we found out in order to lead us to an efficient implementation. So it's interesting that you start from math and then you end up with assembly code. So math affects assembly code. And what do you need to do if you do this thing is that people who do this optimal Boolean functions do them in hardware. So the idea is that you get a function in and it spits out NAND gates. And does AVR have a NAND gate operation? Well, obviously it can compute one, but it doesn't have one in one cycle. So one more thing that you have to consider is that you need a different type of Boolean function. A Boolean function that can do AND, XOR, OR, and NOT. Not a Boolean function with NANDs. So that's what Courtois did as an extension, the Boyar-Peralta heuristic. He grabbed this NAND gate minimization and he translated into AND, OR, and XOR gates. Because in hardware, an AND gate is always implemented with XOR, with NAND gates. So, but that's not the case in software. In software, you can do one cycle for OR, XOR, etc. And this pretty much concludes the presentation on the permutation layer and the substitution layer. There is a key update in the Cipher, and there are some interesting tricks that you can do. So, in the key, you can rotate an 80-bit key register 61 bits to the left. That is what the algorithm says. So, if you want to do that, you better flip the rotation and rotate 9 bits to the right. There are some nice tricks that we try to do in order to improve some speed in the key schedule. And you use 2 move instructions to rotate the bits. And then, once again, you try to avoid shifts. So, rotation, which is pretty much the same background as shift operation. You try to avoid it as much as possible because it's proportional to the shift you want to do. And there is one more thing, that for another thing that you have to do is like substitute like a high nibble of the key. So you craft once again a squared lookup table, but that substitutes only the high part of the key and not the low part of the key. And finally, you have to do a XOR key bits with the round counter. Round counter is how many counters you are right now. And usually you have to XOR this thing here. But if you use it different, so you have like XOR part of the round with one register and part of the round with another register, and this is not good. So in fact, what you do is like changing and doing it at the different points so that you can alternate the steps 1 and 3, and you can XOR just one register because it fits better. That's very architecture specific, but still it's nice. If you
so they don't overlap, basically. They don't span 2 registers.
Yeah, so they don't overlap. It's very application specific, but it's nice if you want to do an exercise at AVR, see why this is actually better than before. And here I have to hand over at Aram, and he's going to give a talk about how making it really small, because my implementation was decent in speed, but awful in size, I would say.
Thank you. Alright, so we're back at the start of the round. It's still present, and this time we're going to optimize for size. This is the procedure I showed you, that Kostas showed you in the beginning. And this is the first step of the round. We are XORing the state with the keys. But we can split this in half to begin with. That helps with basically every part of the algorithm except for key scheduling. But then we need a specific I/O pattern to interleave these 2 halves because of the permutation layer puts them in a certain order. I'll get into that later. What we also showed you in the beginning is that the X, Y, and Z register pairs can be used to address the flash memory and also the registers themselves that are mapped from address 0. So we can use pointers into the registers to manipulate them. This is what I used here to do the round key again. And I can do the whole state, all 8 bytes, by just setting a pointer to the key registers and at the round, read from both at the same time, XOR and put it back in the round. And then going more or fewer cycles is just a matter of changing a constant, this 8 bytes that I need to load. And at the end I put the pointer back at the start of the round, at the state, start of the state. So this is a really powerful mechanism. This is also shorter than what we had initially. It's fewer instructions, and we can reuse it. It's very useful. Then we get to the S boxes, which Kostas already showed you. Instead of expanding them, we're packing them. So we used to have a representation of 16 bytes, where each byte is already filled halfway with 4 bits. So we can cut it in half, and then we need to unpack these again. And this is a bit more tricky. We take the index that we are looking up from and halve it by shifting it to the right, which gives us the carry bit to see on which side of the byte we have to look. So we load the output, and then depending on whether we have the carry bit set or not, we swap the output and then apply the mask to take either side. But we have to be very careful here because this construction is not running in constant time. So we have to add some NOP instructions to make sure that the cycle count is constant whether we take either path. So we can optimize it a bit more. This is what I created initially, but there's a lot of redundancy here. Actually, the smallest way to apply this code to the whole state is to first apply it to the low level and swap it, and then do it again and swap it back. And if we also want to have a procedure that's callable from the high nibble for the key scheduling, as we just seen. We only want to replace the highest 4 bits there. So with this construction, we have only one call to the unpack SBox routine, which means we can inline it. I didn't add the timing correction here, but you can see that it works, and we can still have all our features of calling it as a byte and as a high nibble, and we save the 8 bytes for the table to begin with. Well, the code I showed you though, this is almost is bigger than 8 bytes, but we also need an SBox table, an inverse SBox table for decryption. So then it just works out. We're saving 1 instruction, 2 bytes, so it's still worth it, I think. Okay, now we get to the P layer. I think the easiest way to do it and smallest way in software is to rotate one bit of the register that we are rotating into 4 different output registers. So we splice one bit into 4, and we have 2 bits in each of the output registers. And then we will combine them after we have eaten 4 of these input bytes. This is what it would look like. We have the half state input. We eat 4 bytes, split them bitwise into 4 different registers. That will end up like this. And then we need to interleave these 2 states. But this is only one procedure to do basically all the P layer. We just need to find out a way to do this merging. So here's the device that I thought I should use. We use the stack to push the output values from the P layer procedure so that we can redo a block without relying on the stack. Normally you'd have a procedure call and you'd need a return address stored on the stack, but here we want to have the least amount of code to put something in the RAM and get it back again, so we use the stack, and then we use this construct with state flags, state register flags, to redo it. First time we push all the output, and then we unroll it, and we put the pointers in the correct positions to zip the 2 states back together again. Then finally you have the key register rotation. As Kostas explained, rotation is really expensive, but since I'm going for size, I don't care about that much here. This is actually an optimization for the size optimized version. This would rotate the whole state by 1 bit, and then you call it with an argument to let it loop for a certain number of bits. But again, we can use the indirect register addressing to rotate. We load our rotating value into a dedicated rotated bits register, and then we do a loop and keep rotating into it. We use a special instruction called clear skip if equal. Compare skip if equal, because it doesn't use the state register. It doesn't use the carry bit that we are using to rotate with. And if you would, then it would never work. So it's handy that we have this instruction here. And again, it's smaller than the last one, and it's terrible for performance. So that's why I also included the last one as an optimization. Now, here we are at the end of the presentation with our numbers. We started with the state-of-the-art before we began our project. And here are the new numbers. The latest speed-optimized version has 1,091 cycles per byte. And the size-optimized version has 23,000 cycles per byte. But it's only 272 bytes of code. And the size of the speed-optimized version is about 2K. But then we have the bit-sliced version, which is way faster. It's 370 cycles per byte. We don't have the decryption code implemented for the speed-optimized version. And also it's large, but look at that, that's fast. Then also for the size-optimized version, we have some intermediate configurations. We can have these S-boxes packed or unpacked, but as you can see, it doesn't make a big impact on the size or the cycle count. We can inline the rotation, as I showed you, as an optimization. It makes it a lot faster, about 4 times as fast. And then also, because we were conservative in using our registers, we ended up with just enough free ones to implement 128-bit keys. And as you can see, it's the same size. It would only be a bit bigger if we do inline rotation. Now, for a bit of fun, first let's recap our results. Here's the new graph. Here's the C version. Here's my size-optimized version that doesn't have the speed optimization. Here's the speed-optimized version. Here's another previous work. Here's Kostas' first attempt, and here's his latest attempt, which you can see is super fast. So I think we nicely just pushed the whole graph into this corner, which is the ideal spot to be, and also the interesting spot to research in. Now for a bit of fun, here's the size-optimized version of the present Cipher in AVR assembly opcodes, the machine code as an ASCII banner. Just to prove to you that it's not a joke, here I've highlighted all the different procedures. And I have these printed up as little 2x5 stickers that I can have.
Yeah.
And we also have this working on the Arduino as an Arduino sketch. And you can find all this stuff online on our websites. Here. Yeah, they're interleaved. We have different repositories for all this work. So check it out. And I think that's it.
You mentioned that you add some dummy cycles to make the running constant time.
Yeah.
I assume this is to prevent
I know.
details.
Yeah, it would be a timing
Attack. But how practical would it be if you didn't
Depends.
add those dummy cycles to learn anything about the Cipher operation?
Well, you know as well as I do that it's doable depending on the context.
Right, right. But so let's say we have a piece of crypto code that's running on the x86 machine, the Linux one,
Yeah.
and it's written in C. So it's much harder to be sure it runs in constant time, right?
No. Well, you don't use normal C library functions. You write something that's constant time.
Right. So I
Just
guess
take a look at salt, NaCl. The like chemical name for salt is a cryptography library that has values. It's really readable. And it has primitives like this to do constant time memory comparisons.
Yeah. And as long as you have a cache memory, then I would say that things get hard.
right.
You've read about cache-based timing attacks.
Yeah, AVR tiny doesn't have a cache, or really hard.
Yeah, exactly.
Care about anything
Yeah,
about
much
cache.
more predictable.
Much more predictable. But you put a cache inside in Aram or Kostas or
Yeah, well, if you have a complex operating system running with multiple tasks, then it gets really hard to.
Yeah.
really hard.
Yeah.
But you have like a
But
lockdown.
even if it's time resistant, you can mount differential power analysis. You can go for power analysis.
Yeah, power analysis.
Yeah, and
Yeah, assuming you have physical access.
Yeah.
Yeah.
So, Kostas, when you right before you switched over the presentation, you mentioned that in the P layer you were using 8 registries to swap all the data around. And I wondered if you couldn't reuse the same trick you mentioned before with the flag, just because you were using the entire registry for one registry.
Let's find the slide.
Oh, but you do 8 states.
Can you go to the thing where it said on the left corner key size, and then it goes minus so, further?
Further down or further up? We're
Up means use higher number of flags.
Okay. Say when.
Just I think it was. Yeah, on this slide you mentioned, okay, so if you need to swap positions, you needed to use X amount of 8 registries, right? Or did I misunderstand?
Come again? If I need to swap 2 bits, I need 2 registers to have them stored in 2 different registers.
Yeah, and then you mentioned that it didn't really scale with the amount of registries that you have.
Yeah, we have 32 registers. This is like a toy example. The real thing is 64-bit permutation, not 2-bit permutation. So that would imply 64 registers.
Yeah, so I wondered if you need to swap 2 positions for 2 bits, if you couldn't use the flag trick that you mentioned a few steps down.
The flag trick is nice, but this is faster.
Flag trick. It still costs you cycles.
Yeah, but not size. So you didn't.
Yeah, but this is
exactly. There is the trade-off. Like with the flag thing, you can go really well in size if you do it correctly.
If you move data, you load and store. So that's one move. So one move to a flag would be more or less the same cost.
But you don't move, you just see them differently. You take the representation differently. So rather than doing any actual work, you just say this is now register 1 and this is register 0, rather than before they were reversed. So it's a representation question, and if you do it that way, the permutations become free, because you're just representing them in a different way and then going on in a different representation. That's the one you need.
And it's
Another
also,
question.
yeah.
So you mentioned that the registers are memory mapped as well.
Yeah.
So first of all, this is a confusing concept for
Yeah.
anyone who's not used to that. But
Yeah.
So a load from a memory mapped register, is that the same expense as directly accessing? Yeah. Interesting.
I was really surprised that this exists, And I found it in other similar implementations of crypto on the AVR, similar small codes. And I was like, well, this is cool, I need to use this. And it really, really helped making it this small.
Any ideas to move this to another architecture, other hardware platform?
Which one do you have in mind?
Whatever the people might be using in NFC-like solutions.
Actually, AVR you can buy it as a smart card or as an RFID card, and also as smart cards. The fun cards.
Yeah, the fun cards. Although they're kind of discontinued now.
But it's a popular platform for smart cards and the like, though.
The idea is that if you wanted this on a regular computer on a PC, then you can do AES on the PC. So I would go.
We have a C version of the.
So I would go for MAD. I didn't really care. If you go lower, then you start thinking about FPGAs. But then it's you also have to think substantially in a different way, because you go for hardware. This is kinda in the end of software because it's assembly.
It's like shellcode. Another question?
Have you tried, so these cycles, are they really constant or absolutely? Because I guess on the AVR, a cycle is a cycle, and so did you measure this?
Yes.
Or?
Yes, that's how we found out that we needed this fixed.
Okay.
On a similar, and they should be constant. If you ever sit down and make crypto, it should be constant on AVR.
Do you have any benchmarking tools, or how did you measure this?
We just used the Appel AVR Studio thing.
It's an emulator that does a cycle count.
Exactly.
Okay, you load it in the Arduino, perhaps you could actually measure it in the Arduino, but I'm not sure.
I think it runs slower when you're using that benchmark.
It's certainly running slower, but as long as the tick counter is correct.
Okay.
You just
and slow doesn't even come into it.
No, but if you were testing on a without software, just two hardware and microcontrollers talking to each other, it might be even faster. Because you're not using the debug environment. And it costs a lot of clocks.
Well, it's available as Arduino projects. I highly invite you to play around with it. That's what we need, people using it for fun, and not for serious crypto.
The environment measures only the cycles. It doesn't measure the actual cycles. It measures you have these 3 instructions, 3 cycles. You have this three memory passes.
I'm not sure how it's implemented on our AVR, but it's all to take some extra cycles to push that.
Finally, I think we need a disclaimer. This is a research project, and it's not as secure as AES or anything like it. So we invite anybody to break our implementations, and we have some. Well, we can guarantee that it works as it's designed. And, we have some guarantee that it is in constant time, and otherwise, go nuts and breaking it.
Thank you very much.
Brain.
Okay, thanks. Yeah, there you go.